Okay, so starting a brand new chapter here, moving on to our first uh, foray into calculus, starting to talk about what we call differential calculus. When we're talking about differential calculus, we're talking about usually some kinds of rates of change. Right? The question we're trying to answer is how um, can I measure how fast something is changing, rather how fast um, I don't know how fast the cost to produce an item is growing for a business, or, well, topically, how quickly a disease is spreading. And if we can predict with a model that we have what that rate of change is at any given moment. At the basis of calculus is what we call limits. So that's what we're going to talk about today is limits, continuity, and convergence. So the first thing we want to talk about when we talk about what limits are is usually this example. So we arrive at a bridge. That bridge is 64 meters long, and we come across a troll guarding the bridge, as we do. That gives us the one rule, and that's anytime I go across the bridge, I can only walk half of the remaining distance. So the question then is, do you make it across the bridge? And this is actually a really famous problem. This is one of Zeno's paradoxes, which was developed by the Greeks in the 400s BC, I believe. So let's look at this problem. So we have a bridge. So maybe here is the length of my bridge, and my bridge is 64 meters long. Oops. And every time I cross that bridge, I can only walk half of the remaining distance. So I'm going to start listing out the distances that I have left to cross, or that I crossed. We'll look at it that way instead. The distance that I've crossed every time I cross the bridge. So if I go to cross the bridge once, I've traveled 32 meters. And then if I go to travel again, it's about halfway, I travel 16 meters, and then 8 meters, and then 4 meters, and then 2 meters, and so on. And you can already see that this starts to form a geometric sequence whose common ratio is not 2, whose common ratio is 1/2. And so I can actually model this problem then using a sequence. Right, so the problem can be modeled with, well, based on the data I have here, 32 is my first term times my common ratio to the n minus 1. And this sequence models the distance that I travel every time I travel, every time I cross the bridge. Every time I cross the bridge. Well, the question still remains, do I make it across the bridge? Well, if I extend this series out, or if I pick up from 2, divide it by 2 again, I get 1, and then 1/2, 1/4, 1/8. I never fully make it across the bridge, right? There's no point where I say, yes, I've cleared the bridge. Right, if you were to actually try this problem out and try to walk halfway between a starting and ending point, you would never really clear the bridge. But if I were to add up the infinitely many times I attempt to traverse the bridge, as we learned in chapter 1, this is an infinite convergent series because my common ratio is between -1 and 1. Well, then my sum is 64. So based on mathematics, it would stand to reason that yes, I did cross the bridge. Right? This tells me right here I've completed all 64 meters. But realistically, there's always going to be some little tiny bit that I have left to cross. And that is what we're talking about when we're talking about limits. We're not talking about the actual value, right? We're not talking about, oh, look, I clearly made it across the bridge, or I didn't. We're talking about, well, theoretically, it looks like you're going to cross the bridge, and that's what we're going to care about here. So the limit, or a limit, describes the output of a function as the input approaches a given value from the left and from the right. We have 3 different ways we can write this. if I'm just talking about a limit from any direction, so this is kind of like my general way of writing a limit, kind of like my general limit, right? We're not specifying a direction. Then we'll come back to what that means in a little bit because it's gonna connect to the next two notations I talk about. You see these little subscript pluses and minuses thrown in now. My first one here, a, it looks like a to the negative, right? This is my way of saying from the left. So this is the limit of f of x, right? What the output looks like it's going to be as x, we say, approaches some number a from the left. And that's the key word there, key phrase, from the left. So I'm going from this way, right? From the left to the right. Versus in my third case over here, let's move this over a little bit, that plus is going to tell me from the right. So the limit of f of x as x approaches a from the right. So this way, right? From the right to the left. The key that I've kind of already hinted at is right here. If I'm talking in limits, I don't care what f of a actually is, right? What that number is when I actually get to the value that I'm approaching. I only care about what it looks like it's going to be. So to go back to my bridge example, I don't care whether or not I really make it over the bridge. It just looks like I did, so we're going to say that I did. The way we tie this all together then is to say the limit, I'll do this in a different color so it stands out. I'll say the limit as x approaches a of the function, regardless of direction. That's going to, the way we can actually assign this a value, and we'll call it capital L, the only way we can assign this a value is if and only if the limit from the left is that value and the limit from the right is also that value. Right, you notice here that the limit from the left is L and the limit from the right is L, so therefore the limit overall is L. Otherwise, we say the limit does not exist. So if I consider this graph right here, consider my function here. Here's my function, and calculate the given limits. So a perfect example of this right now is to say f of, as x approaches 3. So, well, where's 3? Here's 3. I'm going to mark it in a dotted line, but it's not an asymptote. It's just to show you, and maybe I won't use a dotted line then. I'll mark it with a solid line. There's 3. We're going to assume, for the sake of simplicity, that it does actually cross the x-axis at this point. It's just my human error. Well, what's the limit from the left? Well, as I'm approaching this graph, I'm starting at the left and I'm moving to the right. As I approach 3 along the x-axis from the left, where's the function going? Where's this function value going? So if I follow the function and I get to 3, I'm getting closer and closer and closer to 0. So we're going to say that the limit as I come from the left is 0. We're going to do the same thing in part B for the right. I'm going to start over here on the right and move to the left. So I'm going to follow my function along until I get to 3. You can see that I'm approaching 0. So we're, for all intents and purposes, going to say that the limit as I approach the function, as I approach 3 from the right of the function, is 0. Well, since both of these match, they're both equal, so I can say that the limit as x approaches 3, regardless of direction, is also 0. Right? That's because parts A and B are equal. I'm not going to rewrite that whole thing. I don't have the space, but you can see up here as x approaches 3 from the left and 3 from the right. They're both the same number, so I can say that the entire thing is the same number. So for negative 3, as x approaches negative 3, and actually I already have negative 3 marked right here because it's an asymptote. I haven't specified a direction, but we know that to calculate this limit when a direction is not specified, I need to look at both sides. So if I look at the limit as x approaches negative 3 from the left, you can see that I'm approaching, actually I'm getting closer and closer and closer to positive infinity, right? This function is getting bigger and bigger and bigger and bigger and bigger, and it's never going to really hit a value, it's just going to keep growing as it approaches that vertical asymptote. So this is actually going to hint at something that we'll talk about a little bit later in the section. But we're going to say that this, that from the left, we're approaching infinity. So what that means will matter and will be explained later on. Well, I also need to look at from the right. All right, we need to look at both sides when we do this. So if I follow my graph, and I follow my graph, and I follow my graph, I'm getting more and more negative as I go down the graph, so we're actually going to say that this approaches negative infinity. And, well, since these are very much not equal, right, these are very much not equal, we say that our limit here does not exist. DNE, does not exist. The limit does not exist. So we're going to contrast that now with, if I consider, just get rid of my other lines here. If I consider what happens right here, when x approaches 1, this is going to get back to the point that I talked about earlier. Remember, same thing, I need to examine, or I need to consider both cases. So I want to consider 1 from the left. And if I do that, if I start from the left and get closer to 1, I'm approaching a function value of 1. Right, I'm approaching this point on the graph, and at this point on the graph, my function value is 1. So we're going to say that the limit is 1, because it's getting closer and closer to 1. So just like my bridge problem, I'm going to say, yeah, of course we get there. I'm going to do the same thing from the right. I'm starting here from the right, moving from the right, getting closer and closer to this point right here. And when I'm at this point right here, when x is 1, my function value is also 1. So I'm going to say that my limit as x approaches 1 from the right is also 1. Well, again, from my theorem, these match, these are equal, so my limit overall is also 1. You may have noticed, however, there's a gaping hole in my graph at x equals 1, which means my function is not equal to 1. My function value is up here. My function value is actually 3. So what does this mean? Well, the reason I bring this up is to prove my point back up here, is to say that the limit doesn't care what the function value is at that point, only what it looks like it's gonna be. By all accounts, from either direction, from this way or from this way, from the left or from the right, the function looks like it's gonna be 1. But the function says, nope, the function is actually 3. So be careful with your notation. Keep in mind that it's only what it looks like it's gonna be, not necessarily what it really is. And that's where you get that discrepancy from the limit as x approaches 1 versus what actually goes on when x is equal to 1. So I won't always give you the graphs. Sometimes I may actually ask you to graph them for yourself. So one thing we're going to talk about next is just how to actually graph these on your calculator. And we know how to graph functions on a calculator. We've been doing this forever. The catch, though, is sometimes you might be asked to graph these functions now with certain domain restrictions. So I have the kind of the format spelled out here, but I'm also going to cover that in a minute just to kind of go over how it works. You notice that they're a little bit similar. You have the same elements, but they work a little bit differently depending on if you're doing this on your calculator, on your graphing calculator, or if you're doing this on something like Desmos, some graphing software. So to do this on the TI-84, we're going to start by graphing our function just like normal. Right, I'm going to go through and maybe I'm graphing, say, 2x plus 3. So if I hit graph, right, our graph is just going to graph like normal. If I want to restrict this to, say, just x values greater than 2, there's a way we can do this, so I need to start by making sure I'm all the way at the end of my function. I'm going to press the divide key and then open a set of parentheses. And I want to restrict my domain to x greater than 2, so I'm going to press my xt theta n key to get my variable, and then to access the greater than, I'm going to do second test. And you see all of my inequality symbols. So I want greater than, which is option number 3, greater than 2. I'll close my parentheses, and if I graph this again, sure enough, it gives me just the part of the graph with the domain I specified. So for something like a piecewise function, so maybe my piecewise function is 2x plus 3, x greater than 2, and then maybe x squared for, well, it would be x less than or equal to 2, so I would second test option 6, close parentheses and graph, and then you get your piecewise function. For something like Desmos, it's similar but a little bit different. So for Desmos, I can still type in my function 2x plus 3. But to restrict it this time, instead of doing my slash notation like I did on the TI-84, I'm going to open up a set of curly brackets and type in my restriction directly. So if I want x greater than 2, I've got it right there. Right? I open up my curly brackets, I have x greater than 2, and you can see that the graph does exactly what I want it to. I can kind of slide up here so you can see it better. And it shows just my function for the specified domain. Likewise, if I wanted to enter in the other part of my piecewise function that I came up with before, less than or equal to 2, in my curly brackets. So in a lot of ways, maybe a little bit simpler, maybe a little faster because you can just type, but the notation itself is slightly different. Okay, so for example, if I'm going to use my graphing calculator, our GDC, as IB calls it, to plot this piecewise function right here. This is where we're really going to need to practice these domain restrictions, is with these piecewise functions, because you can see the domain restrictions are right here. Right? It's built into my function. And then we're going to find the limit as x approaches 1. So I've gone ahead and already plotted it on Desmos and copied it. Remember on your graphing calculator, so if you were to do this on the TI-84, you're going to have your y1 be equal to 2x plus 1, and then you're going to have your division button with your restriction built in, and then likewise for y2. And then if you choose to do this on Desmos, instead of division with the parentheses, I'm just going to have my curly brackets, 2x minus 2, x less than 1. So there they are. So fortunately, I've already done that for you, and it's right off to the left there. Well, I want to find the limit as x approaches 1. X approaches 1, and how I'm going to do that, it's just like I described before. If no direction is specified, I need to check both directions. Well, so we're going to do that from the left. off to the side here, I'm just going to do it. So the limit of f of x as x approaches 1 from the left, if I follow my function, I'm going to start on the left, get closer and closer and closer to 1. So if I follow my function up to 1, I look like I'm approaching 0. So we're going to say that our limit is 0, right? I'm going to get closer and closer and closer to 0, so for all intents and purposes, I made it there. I'm going to say the same thing from the right. So now I'm going to start from the right, I'm going to work my way over to 1. Well, what happens with the function? I get closer and closer and closer to this point. Well, this point, when I'm at x equals 1, I'm at y equals 3. So the limit from the right is 3. So does the limit exist? Well, these do not match. These are not equal to each other from either direction, so we say the limit does not exist. Doesn't really equal does not exist, it just does not exist. Why does it not exist? Because the limit from the left and the limit from the right do not agree.